So hi everyone, I will share my screen. Oop. Sorry, I have to, oops, of course. Okay, is it in full screen? Everything right?
Yes.
Okay, so hi everyone. So today I will be giving a small talk for YPN network, and so it's concerning mainly fast machine learning based prediction of infrasound attenuation. But I will also talk a bit about my previous works and my background. So concerning my background, I am currently a student at ENSTA Paris and currently in a gap year. So during my gap year, I am doing two different, I'm doing two different internships. So the first one has already been completed and was at the CEA in France. And the second one is right now at NORSAR in Norway until July 2022. So concerning my previous work, which was at the CEA in France, I had two different subjects during my internship. But there were some links between, of course. And the first one is concerning the infrasound tracing of intense cyclones in the Mediterranean Sea, which are called Medicanes. And my supervisor was Konstantino Listovsky. So the idea was to use some infrasound signals from the international monitoring system network, and especially from a station which was in Tunisia, which is called S48TN. And the idea was to use a cross-correlation algorithm, which is called PMCC and was developed by the CEA in France, to process these infrasound signals and to try to see if we can make the link between the detections by the PMCC algorithm and the potential infrasound sources. So here you have an example on the right, for example, of the kind of results we can have. So PMCC processes signals, and you can have a lot of different results. You can have the azimuth of the source, you can have the speed of the signals, you can have the time, of course, and a lot of different things. So here we look at the azimuth in function of the time. So here in the solid black line, you have the trajectory of the cyclone in the Mediterranean Sea. And you can see that you have some detections around the path. And the goal was, for example, to show that there is a link between these signals and the potential infrasound sources, which can be thunder or ocean swell, and even volcanoes, for example, in this dashed line. So the second subject on which I worked before was some potential meteo tsunamis caused by these cyclones. So as you may know, tsunamis may be caused by seismic activity, of course, but also by landslides, and also by some variations in atmospheric pressure. And of course, it implies that cyclones may be the cause of tsunamis. So here on the right, you have, well, it's a bit you have a lot of things, but what should be noticed is that you have here an atmospheric perturbation, and with some resonance effects, you can have some waves really large on the shore. And the idea was to use a tsunami code developed by VCA again, which is called Taitoko. So here you have the reference. And my goal was to add a really realistic meteorological source to create the coupling between the atmosphere pressure and the sea surface. And of course, the idea was to use some atmosphere pressure simulations of Medicanes, because I had to study these Mediterranean cyclones. And this is the input. And for example, on the right here, you have the input of the simulation, which is the surface pressure of the sea. And here you can see a depression, which is the cyclone, of course. And then here you have the output of the simulation, and this is the sea level. So in blue, you have a negative sea level, and in red, you have a positive sea level. So you can see that, of course, the cyclone is indeed creating some waves, which can be very, very large, because here you have 20 centimeters in the middle of the Adriatic Sea, but as we saw, you can have some resonance effects, which can lead to large waves. And for an example was to use so these simulations to try to reproduce the Venice exceptional floodings in 2019. And here you can see a comparison between the computations of the code in yellow and the real tide gauges data, which is in blue. And I had to filter that because it wasn't easy to compare. So you have to compare the yellow signal and the orange signal. So it's not perfect, but you see that we had some nice results. So concerning my current work now at NORSAR, so as I mentioned, it concerns the fast prediction of infrasound transmission loss. But what is transmission loss? So the infrasounds are some low frequency acoustic waves, which are under 20 Hertz, and they may be caused by a lot of different sources, and especially the infrasounds, they can be recorded at very large distances from the source. So sometimes a few thousand kilometers. And this is really interesting because then you can detect some events really far away and try to explain it through these signals. So the amplitude decay with distance of the infrasound amplitude is called transmission loss. So an accurate estimation of transmission loss is an opportunity to complement seismic data with acoustic data for remote sensing of sources, because you can have some applications in which you can have some information in the infrasounds and by back projecting infrasounds. Thanks to this knowledge of transmission loss, you can have some nice things. So you have some challenges because, as we mentioned, transmission loss is the infrasound amplitude attenuation with distance, which depends on the winds above the ground. So to compute these attenuations, you have a high computational cost because you have to use some tools like parabolic equations, which are, well, which have a high computational cost, or even more costly tools which try to make a model of or a more precise model of the atmosphere. So here you have the wind profiles, for example, and then you can compute the transmission loss on the ground with these parabolic equations. And this is why what we are studying right now. And the challenge is thus to try to find a way to predict this transmission loss quickly. So to compute these transmission losses quickly, you have two main approaches for fast TL approximation. The first one is to try to make an analytical fitting approach, which is basically a function, which is range dependent. It means that, of course, the function varies with range, which is what we are trying to do. But the problem with that is that you have a limited generalization if you want to use more data, because you made a fit on some data, of course. And the other approach is machine learning tools, because one of the main advantages of machine learning, of course, is that you can compute the solutions really quickly. And the main downsides of machine learning tools is that this is a bit a black box. Like you cannot put a lot of physics inside, of course, and you have a highly costly training. But the benefits are really nice, because of course it's really fast at the end once you train your model. And you have to make an optimization in the architecture of the machine learning process, which is really not easy to do. So if we want to work with some machine learning tools, we have to make an assumption, which is that transmission loss is a nonlinear function of wind profiles along the infrasound path, because machine learning tools they may help to create nonlinear function and to approximate the solution. So this is an assumption that we already tried to do that with, for example, analytical fittings. And you have two different requirements, of course, because you have to create a data set to train the machine learning tool. So you need to have some inputs, which are the wind profiles. As we mentioned, the wind profiles may help, well, they define by hypothesis the transmission loss. And then you have to have the outputs, which are the transmission loss. To compute the outputs, we use the parabolic equations I talked about, which are highly costly. But the goal is that once we trained our model, everything is fast. So this is the idea. And we also have to choose an architecture for the machine learning and its parameters. So this work has been started by Quentin Brissot, who is my supervisor at NORSAR. And he did that for 1,000 kilometer range and simpler atmospheric models with some promising results. And you have a link of a preprint of his paper here. So concerning the architecture, he chose to use some CNNs, which are neural networks. And the idea is that you compute the inputs as an image. And neural networks are really good with processing images and extracting features. So the idea is to use some filters here in blue to extract features and patterns in the image. And then you compare it and try to approximate the transmission loss on the ground here. So once trained, you can have some nice results because, for example, we have 5 decibel average accuracy over the testing dataset, because you have, of course, to separate your dataset between testing and validation, as in a lot of other fields in science. And as you can see, the computational time is really nice, because you can go from 10 seconds to between 10 seconds to 150 seconds to 0.05 seconds to process and to compute the transmission loss. So here you can see that the approximation is not bad, because in pink you have the parabolic equation simulation, and in blue you have the results given by the neural network. However, the idea is to try we see that here it's up to 1,000 kilometers, but this limits the range of possible applications. And some sources are observed globally in the globe. And we can see that we may need to go further and extend this approach to a longer range, to a further range. And my goal in my internship is to try to extend this approach to 4,000 kilometers. So this creates new challenges, because creating the dataset has higher computational costs, as it requires to manipulate really larger data. But one thing really positive is that if we manage to address these challenges, it helps to improve the efficiency of the code. So we have some nice things to do. And of course, we can. I am also trying to explore some new machine learning architectures. For example, recurrent neural networks, because as we see in this image, so here what has been done before was that as we try to extract local and global patterns in our picture here, the thing is that, for example, if we create some variations here, it could impact the transmission loss before that distance, and this is not something we want to do, because it has no physical meaning, because it should be only in one direction. And the winds at range 0 should impact, in theory, all the ranges, but the winds at range, for example, 500 kilometers should impact only what is further 500 kilometers. So this is something we can do with recurrent neural networks. And I won't talk about that in detail, but yes, this is a way to try to put more physics in the machine learning process. And of course, we can try some new parameters, because as I mentioned, trying to find the right architecture for the machine learning tool is, well, it's not really easy. You have to make a lot of changes. And here on the right, you can see some results. This is not on our final dataset. This is a more simple dataset, but as you can see, you can have some nice results. with the machine learning process at these distances. And the applications, of course, could be, as I mentioned, to help to study easily some different infrasound sources, because you can then backpropagate the signal. And it helps to, for example, to have the localization of the source and or the amplitude of the signal emitted from the source. For example, for an explosion, if you don't have a lot of arrays to process the signal, it's difficult to see to find out where the signal comes from. And then if you have a really fast TL prediction model, you can just, well, try in every single direction and see which one could be the best for the source. You can also, it helps also it would help also to study microbaromes, which are some non-linear interaction of ocean surface waves with the atmosphere, which are, well, understudied by a lot of people. And of course, it could help to study some ground shaking, which then may, when you have some ground shaking, you have some interaction with the atmosphere, and it creates infrasound. And of course, being able to understand more the source and the amplitude of the source helps to know the process behind that. So thanks a lot for listening to me, and I guess it's question time.